For the last talk of the afternoon, we will welcome Guilherme Raposo. He's a junior investigator, right, at the Aveiro University. So, please, Guilherme.
Thank you so much. Can you hear me well? Okay, perfect. So first and foremost, well, I have to finish in 45 minutes, so I'll be very fast with this. But I want to thank everyone, especially Professor Crispino, for inviting me here. Thank you. And also the students and everyone that has been around with us. They are been very kind, so thank you so much. Thank you for taking also to Kombu. That was very nice. And well, it's a pleasure to be here. It's my first time in Brazil, actually. It's my first time in Belém, obviously. And well, it's been great. I don't know how you can do it with the heat, but it's really amazing. I'm liking the experience very much. So I was tasked with the quest of giving you this sort of course on compact objects and how to model them. And I will start by giving a brief overview of this. So our goals for this course will be basically to understand what are the frameworks that we use to model compact objects and ultra-compact objects. I'm going to explain what are these ultra-compact objects and compact objects I'm talking about here. But, well, basically, today's lecture will be very introductorial. So I know that there are a lot of diverse backgrounds here. I know people that are experts in the field. I know people that are doing the PhD. I know there are people doing the masters that will eventually become experts in the field, but I want to put everyone in the same page, so this first lecture will be basically for that. And so we are basically going to see what are compact objects, what are the compact objects that we have in our universe, basically how do we model them, what are these exotic compact objects that, for example, Carlos talked before, and Miguel also demonstrated now, and how can we model them, and finally also I'm going to tell how can we test for them. And just to put also some brief context between me giving this presentation and also being here in Pará, I want to go back a few years in time. When I was a student at IST Lisbon, there was this course of topics de relatividade and cosmologia, and there was a second module that I'm going to zoom in that was lectured by someone that you may know, Dr. Caio Macedo, and he gave the course on compact objects. And it was really a very interesting course for me personally. I don't want to put Kai on the spot here, but well, sort of motivated me to pursue more about this research that I'm doing now. And so today I hope to sort of do a short updated version of this course. And well, no problem. And yeah, that's what I'm going to do here. And so let's start with just a very brief motivation about compact objects and why they are important. Well, there are very few systems in physics that connect so many different areas. For example, compact objects, think about, for example, a star. There's a lot of fundamental physics that's going on, for example, plasma physics, the nuclear physics, particle physics, etc. But these stars play a role in the universe, so you also need to consider the astrophysics that is around them. We know that the star, the sun, for example, takes care of the dynamics in the solar system, and you do that for all the universe and different scales. But compact objects specifically are objects that I'm going to define as the ones that have a very intense gravitational field, where the gravitational effects are very strong. And so gravity will be described by Einstein's theory of gravity or any other modified gravity theory that you want. But in this case of this course will be Einstein's gravity. And so this is why we care about these systems of compact objects, is because they see the interconnection of all of these effects. And so let's define what a compact object is, what how compact a celestial body is. And so that circle there is a star, because I'm not very good at drawing. But you know that if this is related with sort of gravitational field, we put here Newtonian's, well, gravitational field that you see there, and then we can try to figure out what macroscopic quantities are used to define the gravitational potential of a finite-sized body. And when I ask this a lot of times, people always say the mass, of course, is there, but there's a second quantity that people sometimes forget, which is the radius. If this is a finite-sized body, this is only valid in the outside of the body. So we need to consider these two quantities always. And so now we can be a bit more concrete. So if you think about a compact object as something very compact, where imagine that I'm in this compact object or in this star with my rocket and I want to get out, it will become increasingly harder for me to escape. And so you can, well, do a simple calculation that we do in school and calculate the escape velocity. And that's what you'll get, this expression that is there. Oops, I have a pointer. This is here. Now, one thing that we can see already is that if you plug, if you put the speed equals the speed of light, you'll get, well, and you solve for the radius here, you'll get the gravitational radius that you now probably know as the Schwarzschild radius in the context of general relativity. But here actually it defines the radius of this dark star that was studied by John Mitchell, well, studied no, but conjectured by John Mitchell in the 18th century. And with that, you can also construct this dimensionless quantity, which is called the compactness. So basically in natural units, so in geometric units that I'm going to use now, it's basically the mass over the radius. And so actually this is the quantity that is used to define how compact an object is. You may have thought about it could be the density, but actually that is not the case. And we can see this. This is a table from a very, well, famous book in this field of compact objects, the book of Shapiro and Tucholsky, where you put here different celestial objects, right? And you can see here in the rightmost column this compactness. For example, for an object like the sun, this is very low, 10 to minus 6. Then you go to objects like white dwarfs. This is a bit higher, but still very low, 10 to minus 4. And then you get to neutron stars and black holes, which have, well, a considerable compactness. And exactly these last two is what, well, only objects with compactness more than neutron star is what I'm going to call compact objects. Now let me give a bit more precise definition. So a compact object is an object which the exterior spacetime contains an innermost stable circular orbit. So basically the radius of this star must be inside of 6 times the mass of the object in units of, okay, in units of the mass and in geometric units. Okay, let me just check if this is working. Okay, let's hope it's working. And okay. And ultra-compact objects are objects that basically the exterior spacetime contains a photon sphere. So in other words, the radius must be smaller than 3m. So I'm assuming you guys know what is the innermost stable circular orbit and a photon sphere, but well, I can just say it very quick. Innermost stable circular orbit, sort of the name implies it, what it is the, well, innermost stable, that the circular orbit that the particle can have. While the photon sphere is basically the unstable circular orbit that light can make, well, or no particles. I'm also going to sometimes talk about exotic compact objects. And in my case, I'm going to say that an exotic compact object is basically anything that is not a black hole or a neutron star. And also, sometimes people talk about black hole mimickers. In my case, they are not the same thing. Black hole mimickers is basically an ultra-compact object that mimics the properties of a black hole. It does not necessarily need to be an exotic compact object. Sorry, the opposite.
Does it have to be an ultra-compact?
Yeah, I mean, I would say so, but in my case, I'm thinking about objects with, okay, compactness arbitrarily close to the black hole. I mean, in some cases, I guess if the compactness is not arbitrarily close, there will be some experiment that you can do that will not imitate a black hole in that regime, right? I guess could be. But so let's just go back to the basics and review the compact objects that we know that you currently know and see in your universe. So this here in the top rows are stars, right? You know in the end product or stellar evolution. the star collapse and will form some other object that will depend on the progenitor mass of the star. In the case of very light stars, they will form white dwarfs that, again, here I'm not considering them a compact object because they are not compact enough. But if the mass is, let's say, between 8 and 25 solar masses, they will form a neutron star. And if the mass is even higher, like, let's say, above 25 solar masses, they will form a black hole. Not this black hole that is here. This was the image of the EHT. This is a supermassive black hole that is in the center of the galaxy. They will form, well, black holes like the ones that we see in LIGO. But, well, there are no images for that one, so I could not put them here. And so let me go case by case, and I'll start with black holes just to simplify. And I like to present this quote of Chandrasekhar as a good starting point. And I'll paraphrase a bit while you guys can read it. But basically it says that, well, he was overwhelmed when he realized that all the black holes that exist in the universe can be represented by an exact solution of Einstein's field equations. And if you think about it, this is remarkable, right? I mean, take, I don't know, two stars that can be completely different in completely different regimes in the universe, and they will collapse and they will form a black hole. This black hole will have the same solution. And these are the black holes that are formed by stars. If you think about the supermassive black holes that are in the center of galaxies, they have a completely different formation process. They have nothing to do with these stellar mass black holes, but they still have the same solution. And so, in the end, this means that black holes are very simple and economical solutions. Well, simple because basically the solutions that we currently have, they only require 2 or 3 parameters: mass, angular momentum, and charge. In the case of astrophysical black holes, we normally neglect the charge. And they are very, well, economical because basically this one single exact solution describes all types of black holes that we have in our universe. So, again, black holes are really remarkable, as noted here by Chandrasekhar. But now we have neutron stars. And neutron stars are a mess. Whenever you sort of start considering matter, things become much more tricky. And in fact, neutron stars cannot even itself be described by one solution throughout the star. They have this layered structure. So for example, neutron stars have, well, some atmosphere outside, but then they have this outer crust, which has this degenerate electron gas and a Coulomb lattice with heavy nuclei. Then after a bit more inside, they have an inner crust, sort of after the neutron trip density, and where basically you have also a gas of neutrons. Inside of that, you have basically an outer core, which has another sort of fluid layer with a mix of free neutrons, protons, electrons, and muons. And in inner core, well, I guess the honest answer is no one knows for sure, because you cannot probe those densities in a laboratory. For example, you see here that this is about 10 to the 15 grams per centimeter cube. You cannot even imagine how big this number is. And yeah, people, depending on the model, can have different sort of matter in that region. For example, you can have deconfined quarks, you can have hyperons, and much other things. So this, in fact, is one of the main open problems in astrophysics. So this is good to contrast the simplicity of black holes with the complexity of neutron stars, and in general, any compact object that you consider that is not, let's say, a neutron star, a black hole, and will be described by some matter or some more complex physics, will in general can be more complex than a black hole. So black holes are indeed very special. That's what I want to highlight here. But now we want to model them. That's sort of the point of this course. And well, modeling of compact objects is already something that we have known how to do for a lot of time. For example, in classical physics, we have known how to do it. For example, take the continuity equation, take Euler's equation or Navier-Stokes equation, depending on the type of matter that you have. Take Poisson's equation, and you can construct basically a solution of the star. Outside, well, basically is Newton's gravitational potential. But now we want to do that in general relativity because we want to study these compact objects. So we sort of need a generalization of these equations that we have here on the left and that you probably are all very familiar with. And if you don't know it yet, you may have also intuition about who done it, especially if you like movies. Because last year there was this movie that you probably know, Oppenheimer. Well, it's a 3-hour movie, but perhaps you have seen it. And this guy was very involved also in the study of the structure of these stars and neutron stars in general relativity, not only the atomic bomb. Specifically here in this scene in the movie, he was conjecturing what will happen to a star that is collapsing under its own gravity. This is actually related with another work that he done, the Oppenheimer-Snyder collapse. Actually, this guy here that is in front of this scene, this represents Snyder. But yeah, indeed, at the same time that he was thinking about this, he was working together with his student, Volkov, on the equations for neutron stars. And this was based on some works of Tolman that were already done in like 5 years before, I think. And so the idea was very simple. Now you know that we have these equations that are Einstein's equations and also the conservation of the stress energy tensor. Then you specify some form for the metric. The most simple one is the spherically symmetric metric, and some form for the stress energy tensor, which is specified, basically it's a perfect fluid. And well, it's consistent with what he was studying at the moment, which was neutron stars. And you get this set of 3 equations. These are basically the generalization of those equations that I had before. The continuity equation, the continuity equation does not matter here because this is time independent, but Poisson's equations and Euler equation. And these, for short, are called the TOV equations. And it's good if you fix these equations because they will appear a lot of times. And so finally, there is one final ingredient that you need. So let me go back again. If you look at these equations, basically you have 4 unknown functions, so mass, density, the gravitational potential, and the pressure. And of course, these are 3 equations. And so to close it, you need this final ingredient, which is the equation of state. I already mentioned before when I was talking about neutron stars. But basically, this specifies the microphysics of the body. And in general, this can be quite complex. And this is sort of important because typically you write it in something in this form here. So you typically specify what is the energy density of your fluid. And this would depend, for example, on the volume of your fluid or the entropy, temperature, etc. But in some cases, especially if the fluid is adiabatic and isentropic, and by adiabatic I mean that the entropy of a fluid element remains constant, and isentropic means that the entropy is constant throughout the star, everywhere. You can write the energy density and the pressure is only a function of this n, which is the number density of particles, or equivalently of the volume of your fluid element. And combining the 2 things, you basically get pressure as a function of the energy density, which is the sort of the form that if you work on these are most familiar with. But the thing that I want to highlight here is that this expression that you are most familiar with is not the most general one. This only happens 1, if it's a fluid, 2, if the fluid is adiabatic, and 3, if the fluid is isentropic. So in general, you cannot always write it in this way. This will become important later on in this course. There's also another thing that is important, which is this fluid bulk conjecture. So this sort of motivates also why they were considered spherical symmetric metric. Because if you consider a fluid that is static and in a statistical flat universe, basically any fluid solution needs to be spherically symmetric. This was proved by Massoud Ulalam in 2007. And this is true for, well, I guess for me, this is not a conjecture, but this is a theorem. But let's say for mathematicians, this is still a conjecture, because this is true if the energy density is positive, and, well, something else that I don't remember, but also a very realistic energy condition, I think. And so, moving on, in general, if you take an equation of state and you try to integrate the TOV equations, you don't have an analytical solution, except in one special case, which is the constant density star. um, which will yield a solution like this. And if you've never done this exercise, I suggest you to do it because it's very, well, instructing. And, well, let's just evaluate what happens when you take this expression and see what happens at the center of our star. So this is the pressure as a function of radius. If you put this, if you put the radial coordinate, let's say, to 0, this term becomes 1, this term becomes what it is. This term becomes 1 again, and then you have this term here. And then you want to see what happens when you increase the central pressure. So we want that this term here to increase, increase, increase. Basically what you need to do is that to put this term to 0. And you see this happens when this, well, when this compactness parameter, this m over r, starts going towards 4 nines. What does this mean? Well, it means that for this constant density star, you cannot go beyond these 4 nines. And in fact, this is more general. This was shown by Bookdahl in, I don't remember when, 29? Yeah, 29. And basically it says that under some very general set of assumptions, this will always hold. Well, general is a strong word here, but the assumptions are, well, that the matter is a perfect fluid with isotropic pressures, that the density and pressure will decrease throughout the star, which is sort of reasonable also, that you consider GR as the theory of gravity, and that the, well, the solution is static. Okay, but let's think about this a bit more. So, does this limit make physical sense? Well, an incompressible fluid, actually, like the one with constant density, will represent infinite sound speed. So we don't expect that any physical object will have it. In fact, you want to consider what is the highest compactness that you can put in your physical object. You want the physical object to be, well, basically viable. And yeah, this is my very ultra compact backpack. Yeah, that's what you're going to do. So for that, you need more realistic, but different types of equations of state. And for that, you don't have any other option. You need to solve the TOV equations numerically. And so we are probably going to do that in the next few lectures, but I'm going to sketch the process that you're going to do. You basically pick a central value for the density, and through the equation of state, you'll get the pressure. Then you put this in your numerical integrator. For example, if you like to use mathematics, it's perfectly okay to do this sort of calculations. And at each point, it calculates the density. And when the pressure is 0, you say that you found the radius and you stop the integration. And well, for the initial value of the potential, you need to do some tricks, but I'll explain this later on because outside of at the boundary of the star, you need to match it with the Schwarzschild solution. So let's look at some other types of equations of state that we have. So you've seen this one, this constant density star, which leads to this Bookdahl limit, as you have seen. But for example, there are other more famous families. For example, families with constant adiabatic index, so families where the pressure is related with, let's say, the baryonic density or the number density of particles through this power law here. And these are, for example, the families of polytropes and linear constant sound speed models. So basically polytropes, well, you probably know them through a different expression, but in terms of the energy density, it looks like this. Sometimes you can also see polytropes written as pressure equals to a power law, where here instead of the number density of particles, you have really the energy density. But let's say that these are sort of the most classical ones. And then, exactly as I mentioned, you have this linear constant sound speed because, well, if you look at this form here, if you take the sound speed as defined by the derivative of the pressure as with the energy density, you have basically this coefficient here is basically the square of the sound speed. And, well, these solutions are interesting. Well, first, for polytropes, it was shown that there are no bounded solutions for n here. So this gamma is 1 plus 1 over n. And so for n larger than 5, there are no bounded solutions. bounded solutions is a fancy word to say there are no stars. While in this second equation of state, this right side here, they are very interesting because they are scaling invariant. So Carlos mentioned that these boson stars have, for example, a maximum mass. This happens also for neutron stars. But scaling invariant objects do not satisfy those types of things because it's like black holes. They have basically one line of solution. Each density is the same solution apart from a scaling. But unfortunately for fluids, these solutions do not exist. There are no stars with this equation of state. But we'll see that later on, what can happen. But you can sort of also do a modification to this equation of state and have a constant sound speed equation of state that always have bounded solutions, which is this affine constant sound speed, where basically you just plug here a constant term. The caveat of this equation of state is that now, unlike fluids, at the boundary of the star, the density is not zero. So there will be some constant energy density there. These rho naught that I represent here. But these are, well, basically this last family of classes includes, well, basically what we currently use to model quark stars, for example. Okay. So now that we have sort of this last model that allow you to get constant sound speed stars, we can answer my previous question of what is the most compact, viable compact, well, this seems redundant. What is the highest compactness that you can get for a star? And, well, basically, you can sort of integrate this equation of state with constant sound speed, and that's what I'm representing here on this plot on the right. So here, these colors here represent the sound speed. When this is 1, is basically the sound speed is the sound speed of, well, is the speed of light, and everything that is in purple is superluminal. So as you see, as this becomes increasingly higher, it reaches this Buchdahl limit. As I've mentioned, the Buchdahl limit is obtained when the sound speed is infinite, basically. But if you now focus when the sound speed is 1, which is sort of, let's say, the maximal that you can get before becoming completely and physical, you get this sort of bound that is here, this 0.364. This is not equal, this is approximate, but it's good enough. And if, apart from that, we impose some radial stabilities, and this is basically saying that you stop this plot at the maximum mass, this decreases a bit, but is about 0.354. Interestingly, these allow for some ultra-compact objects, so objects with light ring, with this equation of state, but there's a very narrow region where this is viable. Now, let's go to other types of equations of state. So, if instead of using these analytical approximations, you really want to motivate it with your nuclear physics model, there's always this set of equations of state that are some tabulated equations of state that you probably have heard. For example, these APR4, SLI, and all these fancy names that you can find. And the thing that I want to highlight here is that, well, first, there are a lot of these models. And second, you can sort of differentiate between two types of models. There are soft equations of state and stiff equations of state. Stiff equations of state typically have, let's say, higher radius for the same mass, while soft equations of state, on the other hand, have lower radius. And through recent astrophysical measurements, specifically with the detection of gravitational waves from neutron stars mergers, people could start put constraints on this equation of state, and basically the soft equations of state are preferred. These are, for example, these APR4 and SLIs, etc. Okay. If you don't like tabulated equations of state, if you do your analytical things, because, well, you need to interpolate between a lot of points, and sometimes that can lead to a lot of mess, you can do, well, something that is in the middle between an analytical polytrope and a realistic equation of state, which are these piecewise polytropes. So basically, you approximate your neutron star or your star by different pieces of polytropes, and typically 3 is good enough because, well, as I mentioned before, you have these different regimes in the star, and for example, in the crust, you have this degenerate gas of relativistic electrons. And now I don't have time to explain, but if you go to this lovely book of Shapiro and Turkolsky, you can see that basically this will correspond to a polytrope with the gamma basically equals to 4/3. So here you need to consider something that is smaller than 4/3. Then in the middle, you have sort of this fluid of non-relativistic neutrons, and this will correspond to a polytropic index of 5/3, sorry, a diabatic index actually. And finally in the crust, well, in the core, you don't know exactly what it is, but if you assume that we have ultra-relativistic quarks and fermions, this will lead to a gamma equals to 1, and so we can construct these three pieces of polytropes and get a good approximation for a neutron star. And actually, I should mention that all these three pieces are soft equation of state that matches very well with what we observed in the gravitation wave constraints. Okay, so I'm gonna, I have a few minutes left because I want to conclude in 5 minutes. So I just want to put this sort of diagram here to represent, well, sort of what I've said until now, right? So this here sort of shows these circles are representing the compact objects that you currently have. So here I'm showing the mass of the compact object in units of the mass. Here on the horizontal axis, I'm sort of showing the radius of the object in units of the mass of the object, so the inverse of the compactness. And you see that in this plot, the objects that we know are basically black holes that are here on the right, with the radius equals to the radius of the horizon. And you have sort of two regimes, the stellar black holes and the supermassive black holes. And, well, neutron stars, well, have only mass of the star, let's say. And then these are sort of the models that I was discussing before. So fluid stars that have casual wave propagation and superluminal fluid stars that can go up to the Bookdahl limit. But basically, all this region here is empty. We don't know what is there. And actually, this region here, we can have models, but the models aren't physical, and they are not very interesting in that sense. So the question that I want to discuss in the next, next lectures of this course is, can we have models of ultra-compact objects that are, let's say, physically reasonable? And, this question of physically reasonable can give a lot of discussion. But let's say, at least they have not superluminal wave propagations. They are sufficiently stable. They can have perhaps some reasonable formation mechanisms. Today we had an example of these compact objects. For example, Carlos mentioned about boson stars, Broca stars. These are families of what we call exotic compact objects that will sort of populate this diagram that I have here, and will complement these black holes and neutron stars that we currently have here. And so, how am I doing on time? Yeah, okay. Do I still have a few more minutes? Or 10 more minutes? Okay, then I'll go a bit further on, and I won't conclude here. So, as I was saying, these are so-called exotic compact objects, and you basically can construct them with a lot of different ways. For example, boson stars were mentioned today, but you can also have anisotropic stars. So instead of an isotropic perfect fluid, you can imagine an anisotropic perfect fluid. You also can have objects that are motivated by quantum corrections to the black hole picture. These are fuzzballs, gravastars, wormholes, whatever you want. And you can conjecture even more, but I'm not going to go into those details here because, well, that will be a longer lecture, let's say. But I just want to end, in this last slide, to motivate why do we care about this. And I sort of divide this into three motivations. The first is the skeptical. So because, in some sense, these exotic compact objects, as we call them, black holes are not anexotic. They are very exotic. In fact, there's this singularity at the center, which for sure points that something is going wrong because the theory of general relativity is not predicting what is happening there, and nothing prevents you to fall there, by the way. You can still go there. So something needs to modify. And there's also, well, if you think that, well, for us observers, it's fine because there's an horizon that's covering the singularity. The horizon itself has some other issues. For example, well, the information loss paradox as the most famous one. This is the skeptical perspective. Now, there's the idealist perspective, like if you are a physicist that you like to study a lot of things, well, you are hoping that there are more species besides these two, because otherwise the universe will be very boring. So you want to study possible other compact objects that are there. And then there's the pragmatic approach, because, well, if you even consider about alternatives to black holes by, well, this is sort of philosophical, but black holes are very difficult or even impossible to test or to constrain because they have an horizon. You cannot even probe until the horizon from infinity. So basically, if you try to constrain everything else, this sort of approach will allow you to validate the black hole model. And so these are sort of the three motivations that I think are important to keep in mind when you want to study this field. And depending on your perspective of life and your approach from physics, you can choose whatever motivation you want. And so I think this is a nice time to finish. I want to finish at 45, and I think it's 45, and leave some time for questions. So thank you, and we'll continue tomorrow.
So, questions?
Well, first, thank you so much for the presentation. And I have a very simple question. It's actually, do you know if there is any willing to construct a analytical approach to understand equations of state of boson stars, or even an analytical approach for the scalar field? If there is, if you know if there is any willing to construct an analytical approach for equation of states of boson stars, for example. Boson stars. It may be in the Newtonian limit, or something like that.
I guess the Newtonian limit are the so-called Q-balls, I think that's the name, right? But, well, what do you mean exactly by analytical? I mean, something that you can, like, write and compute by hand? Of the solution.
But I was saying that I was looking for some reason to write an equation of state as an analytical equation to describe the boson stars, for example, because almost all the solutions that we have are dependent of numerical approaches, and we have only, let's say, graphics to show the features of these objects.
Yeah, so the short answer, I think, is that for boson stars, really you need to do the hardcore mode. But, well, related to what you said, you can sort of define this, well, effective, well, fluid approximation for boson stars, right? I don't know too much about that to be fair. I don't know if in some cases you could construct, let's say, an equation of state of these types for some of them, but in general they are also, let's say, anisotropic, so it will also be, well, quite more complicated. Tomorrow I'm going to talk a bit more about these anisotropic things, so perhaps I'll answer to your question there.
Thank you so much.
You're welcome.
So any more questions? Well, if not, let's thank the speaker again. So we finished the afternoon session for today, and we will see you all tomorrow at 9. So good afternoon.